Hi, let's continue with our section, and in this video I will introduce to you the probability theory. So in this video I just want to introduce a general idea and important concepts that are necessary to better understand the Bayesian methods, and that should be enough for understanding the rest of the course. If necessary, we'll expand and introduce new probability related concepts as we need them. So while probability theory is a major and well-established branch of mathematics, there is more than one interpretation of probability from a Bayesian perspective. A probability is measure that quantifies the uncertainty level of statement. Under this definition of probability, it is totally valid and natural to ask about the probability of life on Mars. The probability of the mass of the electron being around 9.1 times 10 to the power of negative 31 kilogram, or the probability of the 9th June of 1816 being a sunny day in Buenos Aires. So notice, for example, that life of Mars exists or does not exist. The outcome is binary, a yes or no question. But given that we are not sure about the fact, a sensible course of action is trying to find out how likely life on Mars is, since this definition of probability is related to our epidemic state of mind. People often call it subjective definition of probability, but notice that any scientific-minded person will not use their personal beliefs or information provided by an angel to answer such a question. So instead, they will use all the relevant geophysical data or about mass and all the relevant biochemical knowledge about the necessary condition for life and so on. Therefore, by Bayesian probabilities and by extension, Bayesian statistics is as subjective or objective as any other well-established scientific method we have. If we do not have information about a problem, is it reasonable to state that every possible event is equally likely? Formally, this is equivalent to assigning the same probability to every possible event in the absence of information. Our uncertainty is maximum. If we know instead that some events are more likely, then this can be formally represented by assigning higher probability to those events and less to others. Notice then when we talk about the event in statistics, we are not restricting ourselves to things that can happen, such as an asteroid crashing into Earth or my auntie's 60th birthday party. An event is just any possible values or subset values a variable can take, such that event that you are older than 30 or prices of a shattered or the number of bytes sold last year around the world. So the concept of probability is also related to the subject of logic. Under Aristotelian or classic logic, we can only have statements that takes the values of true or false. So under Bayesian definition, probability certainty is just a special case. A true statement that has probability of 1, a false statement that has probability of 0. We will assign a probability of 1 to the statement. There is Martian life only after having conclusive data indicating something is growing and reproducing and doing all the activity we associate with living organisms. Notice, however, that assigning a probability of 0 is harder because we can always think that there is some Martian spot that is unexplored, or we have made mistakes with some experience or several other reasons that could lead us to fully believe life is absent on Mars, even when it is not related to this point is conclusive. stating that we should reserve the use of prior probabilities of 0 or 1 to logically true or false statements. Interestingly enough, Richard Coase mathematically proved that if we want to extend logic to include uncertainty, we must use probabilities and probability theory. Bayesian theory is just a logical consequence of the rules of probability we will see soon. Hence, another way of thinking about Bayesian statistics is an extension of logic when dealing with uncertainty, something that clearly has nothing to do with subjective reasoning in the pejorative sense. People often use the term subjective. So to summarize, using probability to model uncertainty is not necessarily related to the debate about whether a measure is deterministic or random at its most fundamental level, nor is related to subjective personal belief. Instead, it's a purely methodological approach to model uncertainty. We recognize most phenomena are difficult to grasp because we generally have to deal with incomplete or noisy data. We are intrinsically limited by our evolution, scum, primate, brain, or any other sound region we could add. As a consequence, we use a modeling approach that explicitly takes uncertainty into account. So let's talk about defining probability. So probability, that's a number in the 0 to 1 interval, that is numbers between 0 and 1 including both extremes. So probabilities follow a few rules. One of these rules is the product rule. So we have the probability of A and B. So we got probability of A or B times the probability of B. So we read this as follow: the probability of A and B is equal to the probability of A given B times the probability of B. So B expression represents the joint probability of A and B. The B The probability BA expression is used to indicate a conditional probability. So the name refers to the fact that the probability of A is conditioned on knowing B. So for example, the probability that the payment is wet is different from the probability that the payment is wet if we know or given that it is rain. A conditional probability can be larger, smaller than, or equal to the unconditional probability. So if knowing B does not provide us with information about A, then probability of A or B equal probability of A. This will be true if A and B are independent each other. In contrary, if knowing B gives us useful information about A, then the conditional probability could be larger or smaller than the unconditional probability depending on whether knowing B makes A less or more likely. So let's see simple example using a fair six-sided die. So what is the probability of getting the number 3 if we roll a die? So P die equals 3. So this is 1 over 6 since each of the 6 numbers had the same chance for a fair six-sided die. And what is the probability of getting the number 3 given that we have obtained the odd number? So we got P die equal 3 or die equal odd. So this is 1 over 3 because if we know we have an odd number, the only possible number are 1, 3, and 5, and each of them has the same chance. Finally, what is the probability of dice equal 3 or die equal even? So this is 0 because if we know the number is even, then the only possible ones are 2, 4, 6. thus getting 3 is not possible. As we see from this simple example, by conditioning on observed data, we effectively change the probability of events, and with it, the uncertainty we have about them. Conditional probabilities are the heart of statistics, irrespective to your problem being rolling dice or building self-driving cars. And that is all in this video, so I hope you enjoy it, and I will see you in the next video.